Welcome to this lecture in the ongoing series of lectures in real analysis. We are starting a new module which is about infinite series. So far what we can do is add finite sums. That's nothing very surprising. But the gadget of analysis, all this machinery that we have developed like convergence and all, this allows us to talk about infinite sums in a coherent and logically consistent way. And this is truly an analytical device that we can talk about infinite sums. Everything so far in some sense that we have done is kind of algebraic. We can talk about differentiability of polynomials, their surds and their ratios. It's almost like very algebraic thing, but this infinite series business leads us to talk about genuinely non-polynomial like functions, like the exponential function. So that is a long story and this is just the start of it. We will get there, but whatever be the case, let us start with the module. So first let me recall a very well-known paradox called the Zeno's paradox, which says that suppose we have this line, let's say the length is 1 meter, and imagine a very small insect which starts here and travels with constant velocity, let's say 1 meter per second, and well, of course, then the insect will reach the destination in 1 second. But the paradox says the following. So you consider, there must come a time when the insect is halfway through. There must also come a time when the insect is 3/4 of the way through. And then there must come a time when the insect is, I think this 7, 8, 7, 9. I'm sure you get what I'm trying to say. So the insect has all these intermediate positions, and it seems that, well, then the insect should never reach the destination because there are infinitely many checkpoints that the insect needs to cross. So this is a paradox. This is not a contradiction. This is something that confuses our mind. But with the gadget of infinite series, we can kind of resolve this paradox. So okay, let's get into the formal definitions. So we have some sequence of real numbers. Then the symbol that we associate, given any sequence of real numbers, this symbol is called the infinite series. So any sequence, you can build an infinite series. So far, this is just a notation. There's no meaning, nothing more than just the symbol associated to this phraseology. All right. Now, this symbol can also be written in this fashion, but it's the same. Again, there is no content added. It's just a change of notation. I would also like to emphasize that one may also drop these limiters and just simply write sigma n an, assuming that the reader is not getting confused. Or in fact, one may be even more lazy and write this. I would avoid doing this because then this kind of doesn't make any sense. There is no summation running over. This can get very confusing. This I may do several times, but I hope that the limits will be clear, and mostly the limits will be 1 to infinity. When the limit is not 1 to infinity, one could also have a sequence starting from 0 rather than 1. It may not be indexed by natural numbers, it may be indexed by whole numbers. So then instead of writing n equals 1 to infinity, we may write n equals 0 to infinity. So all those things will not confuse us, but I just wanted to plant a flag there. So once we have an infinite series, this symbol, we can associate genuine real numbers by considering what is called the nth partial sum. So for each natural number n, we get a real number Sn, which is defined in this fashion. You just sum up the first n numbers, and this is a finite sum. So this has a genuine meaning. Rather than just being a symbol, this is a real number, while this is so far just a symbol, as I've marked here. So it's a genuine real number. So to summarize, whenever we are given an infinite series, we can associate a sequence of real numbers called the nth partial sum. So this is a sequence generated out of a series. And now we can discuss what is meant by convergence and divergence of this thing. So, so we say that this infinite series is convergent, or it converges if the sequence of nth partial sums converges. Okay, and we say it diverges if the sequence of nth partial sums does not converge, or in other words, it diverges. So very simple. And if this thing converges, and let's say the limit of the partial sums is this real number s, then we write this equality. So this symbol has now been associated with a real number, which is the limit of the nth partial sums. Of course, this happens only when this thing converges. Otherwise, we can't get any such real number. All right, so this is just some definitions so far. And now let us take an example. So assume we have some real number a, whose magnitude is at most strictly less than 1. And we have the series. So the nth term in the series is this guy, and note that the nth term is decreasing in magnitude since mod a is less than 1. A square, a cube, this is a strictly decreasing, when you talk about magnitude, this is a decreasing sequence. So what I'm saying is that mod a square, mod a cube, this is a strictly decreasing sequence because of this hypothesis. And we want to show that this is convergent. This series is convergent. This is called the geometric series. Any such series is called a geometric series. Okay. And I'm sure we have seen a proof of this in our high school, but I will repeat that proof. Let me add a page. Right, so how do we do this? So here is the proof. So let S be this nth partial sum, which goes from 1 to n, a to the k minus 1. So this is the nth partial sum associated to the series written above, and which gives that a times Sn is summation k equals 1 to n a to the k. Okay, this is same as, and this is a very simple observation, that this is same as k equals 2 to n plus 1 a to the k minus 1. Nothing really happened. So if we subtract the two things, we get k equals 1 to n a to the k minus 1 minus summation k equals 2 to n plus 1 a to the k minus 1. And if you just cancel out the common terms, we will get two things here. So k equals 1 term survives, which is equal to 1. The term corresponding to k equals 1 is actually 1. And here we will see a to the n. Because the term corresponding to n plus 1 survives, everything else gets cancelled out. So corresponding to n plus 1, we get an a to the n. So this gives us that Sn into 1 minus a is this guy, 1 minus a to the n, which implies Sn is 1 minus a to the n divided by 1 minus a. So if this is Sn, then clearly limit n tends to infinity, Sn is 1 upon 1 minus a. Simply because this guy dies down, and here is where we use the hypothesis that mod a is less than 1. So we have that, and this means, what this means is that this geometric series this is equal to 1 upon 1 minus a. And I'm sure we have seen this formula in our high school or at some point in our lives. Anyway, so this settles Zeno's paradox. So what we have is we have an insect which starts at 0 and ends at 1, and let's say it moves at 1 meter per second. Then how much time does it take to reach halfway through? It takes these many seconds. Then how much time it takes to reach 3/4? So it's already here, and then it takes half of half much time to reach there. So this is how much time it needs to reach the second checkpoint, and you just keep going and dot dot dot. So we see that this is a geometric series. It is so it is not starting with 1, but it is starting with a half, and this is also going to be it's the limit of partial sums will exist even in this case, and it will turn out to be equal to 1, because what you can do is you can just take half common, so to say. And I'm being a little bit informal here, but I hope you don't get confused. So the above thing is this, and this we just calculated. The thing in brackets is something that we just calculated. It is 1 upon 1 minus half. So the thing turns out to be 1. So what it says is that the amount of time the insect takes to reach from 0 to 1 is actually 1. So despite it taking or crossing infinitely many checkpoints, despite the process taking infinitely many steps, it doesn't mean the process will take infinite time. So that is the resolution of the paradox. The process may take infinitely many steps, but the time the process takes may still be finite. An infinite series is what models it, or at least one way to model it. Alright, so now here's a very interesting, or rather, although very basic fact about convergent infinite series. It's very useful. So given an infinite series, how do you decide if it converges or not? This is one test for it. It is not a perfect test, meaning if you don't see this, that doesn't mean if you don't see this, then that does mean that the series does not converge. But just because you have this doesn't mean that the series converges. So okay, what is the statement? The statement is that you start with any convergent series. Sorry, this is not written correctly. What I should write is, let this be a convergent series. So we start with a convergent series. We want to show that the individual terms, the summands, so to say, converge to 0. This is just a one-way implication. Convergent series implies this happens, but the converse is not true, and we'll give an example to show that. But right now, let's just prove it. And here is the proof. So let Sn be the nth partial sum. And we know that by the fact that the series converges, we know that Sn converges and say Sn converges to some real number S. But note that if Sn converges, then this sequence, let me write limiters here also. So if Sn converges, then the sequence that I just wrote also converges, because it's just a subsequence of the original thing. And it converges to the same thing. And Sn plus 1 goes to S as n goes to infinity. So therefore, Sn plus 1 minus Sn, this difference sequence, this converges to 0. Or rather, I should write S minus S, which is equal to 0 as n goes to infinity. Which implies that An plus 1 goes to 0 as n goes to infinity. But that's the same as saying that An converges to 0 as n goes to infinity. And that's it, that's the proof. Okay, very simple. So if you are given a series and you see that this fails, you know that it does not converge. And now for a counterexample for the reverse direction. Here we have a series where the individual terms, the summands, they do go to 0, but we will show that this is actually a divergent series. Okay, so here is how we will do it. So we have 1 plus half plus 1/3 plus 1/4 plus 1/5, 1/6 plus 1/7, and so on, dot dot dot. So this is the infinite series that is written over here. And here is a very simple observation. The first term is of course greater than or equal to half. The sum of the next two terms is greater than or equal to 1/4 plus 1/4. The sum of the next four terms is greater than or equal to 1/8 plus 1/8 plus 1/8 plus 1/8, and so on. So here we have 2, then we have a 4, then 8, and then 16, and it will progress like that. So the 2 to the, if you just decode what has been written here, you'll see that the 2 to the n, so if S is the sequence of, if Sn is defined by this equation, meaning Sn is the nth partial sum, then the above says that S of this thing, meaning if this is your capital N, then S sub capital N is at least 1 times half plus 2 times 1/4 plus 4 times 1/8 up to, this will go up to n times. So this will be 2 to the, let me shift this to another line. This will be 2 to the power n minus 1, 1 upon 2 to the power n. So let me just see if this is not off by some counter. So for n equals 1, this will give me greater than or equal to half, which will, yeah, this is correct. So you just using this observation, you can verify that. But what is on the right hand side? On the right hand side we have half plus half plus dot dot dot. How many times? Is it n times or n minus 1 times? It is n times. So this is happening n times, which is equal to n by 2. So the 2 to the n minus 1th partial sum is greater than or equal to, is strictly greater than n by 2, and therefore this does not converge. This sequence does not converge. Which implies that this sequence also does not converge. Why? Because this guy is a subsequence of this guy. So if this had converged, then this would also have converged. Sorry for the wrong English. So this, which is same as saying that this series is not convergent or is divergent. It's a very fundamental example of a divergent series. Okay. And now we have a characterization of convergence of infinite series, and it is also pretty useful. So we start with an infinite series, and then the following two things are equivalent, which is first says that the series is convergent, and the second is some technical looking thing which says that you fix an epsilon greater than 0, then there is some natural number such that if you pick two indices exceeding the natural number n, then the sum of the series for the interval between m and n, you're summing over the summands which lie in this range, that is less than epsilon. So it's sort of like once you cross a certain threshold, no matter how much things you pick up and sum up, you're not going to get much mileage. You're not going to exceed a certain value. So I hope you get what this is trying to say, and let's prove it. So it is, let's see, 1 implies 2. Why is that? Let me just do this. Yeah. All right. So why 1 implies 2? So again, we have Sn is the nth partial thumbs. And since 1 holds basically by 1 precisely means that Sn converges. Therefore, this is a Cauchy sequence, because convergent sequence and Cauchy sequences are the same, exact same objects. This is a Cauchy sequence, which means what? Which means that there exists some natural number n such that if I pick m if I pick that, I get Sm minus, or let me write Sn minus Sm is less than epsilon. So before I had said it, I should have fix an epsilon greater than 0, and then there is some n such that blah happens. It is exactly from the definition of a Cauchy sequence. So what does this say? This says that summation k equals m plus 1. I can write this here. It doesn't really change anything. Let me write an equality sign here. So k equals m plus 1 to n a k. This is less than epsilon. So fine, this looks a little bit different from 2, but I will change this statement. Although it doesn't really change anything, let me just write a plus 1 here. It's better that way. And let me also correct that. I think this is the best way to express it. So I didn't really change much. All I did was just a little bit of adjustment for the sake of exposition. Okay, so we have this is the statement of 2, that there is some n such that whenever you pick things like this, you get that. That's the statement of 2. And if you just reverse the steps in this argument, you will get 2 implies 1. So 2 implies 1 is an exercise. Very simple exercise. Right, so that is Cauchy's criterion for convergence. And as we go along, we'll see how, some more examples of convergent series. Right now we have just seen the geometric series as the only example of a convergent series, but in the subsequent lectures we'll see more examples. So maybe you can also try to figure out this, although we'll do it in the future lectures, but you can try to figure out why question does this converge? Answer is yes, it's very classical. So in the subsequent lectures we'll see that this converges, and a whole family of such things converges. Anyway, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.